Good afternoon. So today we are going to discuss about eigenvalues and eigenvectors. Here a matrix A that represents a simple linear transformation is shown in the figure. Uh, the transformation is represented along the yellow line. After the transformation, our basis vector I and j move per usual per the definition of A. However, holding the pink line constant, the yellow line gets knocked off. Interestingly, the green line representing I still perfectly overlaps with the white line that went through the transformation. Moreover, there was actually a span that was originally on the line which is y equal to minus x, where the yellow arrow remains on the line. In fact, all the hypothetical lines in our original basis space, the only vectors that remain on their original lines after transformation A are those green and yellow lines. These lines are called eigenvectors, and the points that fall on these lines before the transformation are moved along them. They are called as eigenvalues. More broadly, we can state that eigenvectors of a linear transformation A are the vectors that stay put when the undergoing transformation through possibly scaling towards or away from the origin by some factor that is their eigenvalues. Now let's interpret the eigenvalues and eigenvector. Looking at the 3D perspective, um, what happens when you got a flat cube? Then impose some linear transformation to that cube and that rotates in a space. The axis of rotation clearly is in some clear-cut yellow line representing an axis. But the three-dimensional vector is represented as a pink line. If you are able to calculate the eigenvalue of 3 by 3 matrix A, you would find a pink line below as it does not move. You would also find that it had a corresponding eigenvalue of 1 as the line doesn't undergo any stretching or shrinking whatsoever. Considering the transformations, up to this point of series, we have always considered the matrix of a linear transformation A in terms its columns and thereby where it sends our basis unit vector I and j. However, another way to consider this transformation is via eigenvectors. Consider an example. If we are found and plotted our eigenvectors as below, we give ourselves an excellent orientation to understand the transformation instead of trying to grok the essence of transformation relative to our starting vectors. We can think of establishing a skeleton that stays structurally sound and compressing or stretching the skeleton appropriately all other points transform as a byproduct. Symbolically, let's recall what is important. The following equation of calculating eigenvalues of eigenvectors are represented mathematically. The transformation matrix is A and V is the eigenvector, lambda is the eigenvalue. So we can write eigenvector and eigenvalue as AV equal to lambda V. Applying algebra to this equation, and we can write and we can modify this equation as uh, moving lambda V to right hand side and multiplying it with an unitary matrix, taking vector V as common. Now we have A minus lambda I into V, which is equal to 0. The determinant of A minus lambda I will be equal to 0. And by the formula of the determinant, we can put a strong algebra emphasis on our linear algebra when finding lambda values which holds true. Now let's discuss about eigenbases. Now what if the basis that defined our orientation was our eigenvectors? It is not hard to see that the adding minus lambda term to each element on the diag and setting equal to 0 would reveal the eigenvalues to be just values on the diag. Similarly, that the columns of this matrix are the corresponding eigenvectors. This has the convenient property that taking arbitrary many powers of this matrix involves only 4 calculations exponentiating on the diag. Now let's move to another term, diagonalization. An awesome result of eigenvectors of a transformation only expand and contract only the same lines, that is doing a change of basis on our transformation A to a space defined by eigenvectors, which will given by the definition of diagonal matrix. Thank you.